This is Yuta Michimura from the University of Tokyo. Today I'm going to talk about DANCE, which is a dark matter axion search with ring cavity experiment. As many of you know, dark matter has been a mystery for almost a century, and dark matter was originally suggested in 1930s from measurement of galaxy rotation curves. And nowadays, we know that this dark matter accounts for 80% of all the matter of the universe. And this standard model of cosmology is amazingly consistent with various observations, but we still don't know what dark matter is. And dark matter is not included in the standard model of particle physics. And there is a lot of dark matter models. And in the mass range, there are almost 90 orders of magnitude of different kinds of dark matter models, from 10 to the minus 30 gigaelectron volt to 10 to 60 gigaelectron volt. And the lightest end is called ultralight dark matter, and the heaviest end is, for example, primordial black holes. But the searches were focused on WIMPs, which is weakly interacting massive particles, which is in this range. And there have been a lot of large-scale experiments to try to detect these WIMPs, but it has not been decisively detected yet. And this motivates us to search for other candidates with new ideas. And our focus on is this range, ultralight dark matter with laser interferometry. So bosonic ultralight field or ultralight dark matter are well motivated from cosmology because it behaves as classical waves with frequency which looks like this. And laser interferometers are sensitive to such tiny oscillations, which was clearly demonstrated by LIGO detection of gravitational waves. And laser interferometers are sensitive in 100 Hz range. So this means that this is sensitive in the range of 10 to the minus 12 electron volt. And people have proposed various searches for dark matter, ultralight dark matter with laser interferometers. For example, by searching for tiny forces acting on mirrors, you can search for vector dark matter, and LIGO-Virgo-Kagra collaboration has already searched for these kind of dark matter candidates. And also, scalar dark matter can be searched for by searching for mirror thickness changes. And Geo600 search was already done. And by looking for speed of light changes or polarization changes, you can search for axion dark matter. More recently, by looking at metric changes, you can also search for spin-to dark matter, which is proposed by this paper. And today, I want to talk about the tabletop experiment, DANCE, to search for axion dark matter. And this plot shows previous limits for axion dark matter, especially by searching for axion-photon coupling. And x-axis is the mass of the axion, and the y-axis is this axion and photon coupling. And shaded region are excluded region. And many of the experiments search for axion-like particles by looking for this kind of axion-photon coupling, especially by using magnetic fields. And my talk is this proposed experiment, which do not use magnetic field. You can search for axions without magnets by looking for polarization modulation. This is because if axion-photon coupling exists, this gives different phase velocity between left-handed and right-handed circular polarizations, which can be written like this. And this is in circular polarization plane, but if you convert this into linear polarization plane, this phase velocity difference creates a modulation of linear polarization, and the linear polarization rotates like this. In other words, for example, if you inject S polarizations, this gives P polarization sidebands around the carrier. And by looking for the frequency of this sideband, you can search for the axion mass, and from the amplitude of this sideband, you can search for axion photon coupling, which is this one. And this can be done without magnetic field. So this idea is pretty simple. If you have a laser with a linear polarization, and if you inject this laser into some polarization monitor, you can look for this polarization modulation. But if you want to do this is in a tabletop experiment, you want to amplify this polarization modulation. And to do this, we usually use a linear cavity. But with a linear cavity, your polarization modulation is flipped by mirror reflections. So actually, this kind of effect is cancelled out with a linear cavity. So what we proposed is to use a bow tie cavity, which looks like this kind of a bow tie shape. And now you have two reflections on each end, so it preserves parity, and this saves polarization from flipping on mirror reflections. And with this, you can amplify the axial signal. And we estimated the reach for this kind of experiment. And if the cavity, this cavity experiment is limited by shot noise, and if you do a 1 year observation with 10-meter dense cavity, you can search for in this range. So you can actually improve the sensitivity compared with previous experiments. So And actually, this dance experiment has a strong connection with cosmic birefringence. Cosmic birefringence is a polarization rotation of cosmic microwave background, and people have recently found a hint of actual polarization rotation of cosmic microwave background. And if this can be explained by axion in a dark energy range, maybe there is another axion which can account for dark matter. And this kind of two-axion model can explain both cosmic birefringence and dark matter in the mass range of dance. For example, in this Obatekun's paper, dark matter axion can be in this range or this range or this range, depending on the other parameter of other axions. And you can actually search for this kind of model with dance sensitivity. And more recently, there have been a suggestion of dynamical dark energy from DESI observations, and this also can be explained by axion dark energy. So existence of axions are now pretty well motivated from these kind of experiments, and we are also excited to search for dark matter axions. And this is the status of dance. We did the first demonstration of this dance experiment in 2021, which is reported in this paper. We did a short observing run with a prototype experiment, and we placed upper limit like this. And now we are gradually improving the sensitivity, and our reach with current sensitivity with 1 year observation is something around here. So we are like 3 orders of magnitude away from the cast limit. But over 3 years, we have been improving by around 4 orders of magnitude. Let me briefly explain our first data analysis result from 2021 run. We used 24-hour data from this run, and actually from the initial analysis, we found 551 candidates, which looks like this. So this is SNR as a function of frequency, and this blue one is a measured SNR, and this orange is SNR threshold. So actually we found 551 candidates above SNR threshold. This analysis method is outlined in this paper. And after this, we did a veto analysis, we first did a consistency better. So we used different set of 24-hour data. And if this is an actual dark matter signal, the frequency should be the same for different sets of data. But if not, we can actually exclude this candidate. And after that, we did a Q factor veto, because if it's a dark matter signal, this line should have the Q value of around 10 to 6 from the velocity dispersion of dark matter particles. And there were remaining 7 candidates after this veto, but all were multiples of 40 Hertz, and which was found to be some mechanical resonance, which is also can be seen in the laser frequency control signal. So we rejected these remaining 7 candidates. So we can veto all the signals, all the candidates, and place the upper limits, which looks like this. So upper limit from this 2021 was not as stringent as we expected. This was because simultaneous resonance of 2 polarizations were not achievable with this prototype experiment. So to enhance the signal, simultaneous resonance of S polarization and P polarization is necessary, because inside the cavity, so this line shows the cavity resonance as a function of frequency, and if you inject a carrier light, which is on resonance of the cavity, this carrier signal is enhanced. So the amount of the sideband, P polarization sideband generated from axion dark matter coupling is also enhanced. And this sideband can be enhanced if this is within the cavity line width. So if P polarization and S polarization are both simultaneously resonant, both signals are enhanced, so you can achieve this kind of broad sensitivity in axion mass and axion photon coupling plane. But P polarization and S polarization, if they are not simultaneously resonant and it has a set resonant frequency difference, even if the carrier light is enhanced, the sideband light cannot be enhanced. So the sensitivity at low frequencies will be degraded. But if the axion mass happens to be in the same as the frequency difference between S polarization and P polarization resonance, this sideband can be enhanced, so you will have a dip in the sensitivity curve. But at the low frequencies, the sensitivity is not as good as simultaneous resonance case. So this was one of the reason why the upper limit from 2021 run was not as good. So the reason why we had the resonant frequency difference between S polarization and P polarization is because you have near 45 degrees incidence on cavity mirrors. So because this is not a normal incidence, you will have a reflection phase difference between S polarization and P polarization, which leads to resonant frequency difference between S polarization and P polarization. But this reflection phase difference can be tuned if you change the laser wavelengths. So we developed our external cavity diode laser, which is abbreviated as ECDL, which can tune the laser wavelengths, and we actually demonstrated that the resonant frequency difference can be tuned by tuning the wavelengths. This is showing that resonant frequency shifts as a function of laser wavelengths, and at 1067 in this case, S polarization and P polarization resonates at the same time. So you can actually enhance the sensitivity in low frequencies. Our principle and demonstration of this kind of experiment is reported in this Takedara-kun's paper, which should be appear on arXiv today. So we talked about the answer experiment, which is a tabletop experiment. But you can actually also do this kind of axion dark matter search with gravitational wave detectors like LIGO in the US or Kagra in Japan. We actually installed polarization optics in Kagra to search for axions. And since gravitational wave detectors utilize linear cavities, At low frequencies, actually the sensitivity is not as good compared with tabletop experiment, but at high frequencies, where axion frequency and time it takes, the inverse of time it takes for the light to go back and forth is the same. So in other words, if the round trip time equals to add multiples of axion oscillation period, actually sensitivity is enhanced. So you will have a sensitivity enhancement at high frequency at multiples of free spectral range. And for example, color sensitivity is in this blue curve, and LIGO is this red curve, and Cosmic Explorer is this orange curve. So if you have a different cavity length, you will have a different sensitivity curves at high frequencies. So in summary, laser interferometers opens up new possibilities for dark matter search, especially ultralight dark matter search. And Dan's experiment is to search for axion-like particles by searching for polarization modulation of light with optical ring cavity. And this search can be done without magnets. And prototype experiment Dan's Act 1 is underway. And actually the first result from 24-hour data is released as this paper. And now we are working on further sensitivity improvement using wavelength tunable laser to tune the birefringence of the cavity. Thank you very much.